We take it for granted that our universe contains planets, stars, and galaxies because those are the things we see. But the only reason these big structures exist is because of the nature of nothingness, empty space. But to understand why, we have to go back to the beginning, the very beginning, the Big Bang. You know, I always thought that in the Big Bang, the observable universe started as a point and then just expanded steadily, more or less, to the point that we're at today. But that's not actually how it happened. There were 4 different phases in the universe's expansion. To start, it was expanding steadily. But then, after just a tiny fraction of a second, the expansion just blew up and the whole universe increased in size by like 10 to the 26 times in a very short period of time, and that period is known as inflation. And then, just as abruptly as it began, inflation stopped. And after that, the universe continued expanding, but at a decreasing rate. So the expansion of the universe was actually slowing down, which is exactly what you expect if the universe is full of massive objects that gravitationally attract each other. But then about 5 or 6 billion years ago, the expansion of the universe started speeding up again. And this is thought to be caused by dark energy, an energy tied to space. So before that time, there was enough matter, the matter density was high enough, that it was pulling everything back together, slowing down the expansion. But once the universe reached a critical size, well, then there was enough dark energy to start pushing things apart. And that is the phase that we're still in. The expansion of the universe is accelerating. Now, this story doesn't really explain the formation of galaxies until you tie in the nature of nothingness. Now, ordinarily, we think of everything around us as made of particles, of atoms and electrons, but our best theories of physics are actually field theories that say all of these particles should be seen as just excitations in fields. The word field always gets me because it makes me think of, well, fields. But a field is just something that has a value everywhere in space. So every subatomic particle has its own field, an electron field, an up quark field, a down quark field, a neutrino field, and so on. And anywhere there's an excitation in this field, that is some energy in the field, well, that is where we will observe particles. So out in completely empty space, well, the values for all of these fields are basically 0. But here's the thing. It's impossible to make a field perfectly flat and 0.
You cannot take a quantum field and make it completely quiet. You know, it's the Heisenberg uncertainty principle. It says you can't take a particle and pinpoint it to exactly 0 energy. Likewise, you can't take a quantum field and make it exactly flat everywhere.
Now this is important because ordinarily these fluctuations are really, really tiny and they only affect subatomic processes. But during that period of inflation, the universe expanded in size so rapidly and so incredibly that those tiny fluctuations got blown up to the scale of the observable universe. Now, without them, we think the matter distribution in the universe would have been completely homogeneous, completely uniform. And that means the gravitational force on any object in the universe would have been the same in all directions. Which means nothing would ever have collapsed into the big structures that we see today. But thanks to these fluctuations, there were slightly denser and less dense regions, and of course the denser regions had stronger gravitational fields, so they pulled in the matter from around them, and that clumped together the matter into huge gas clouds that would go on to be the galaxies that contain the stars and the planets and the things we know today. You can actually see the imprint of these quantum fluctuations in the leftover radiation from the Big Bang, the cosmic microwave background radiation.
The quantum fluctuations in the fields were amplified to big classical fluctuations in the density of matter from place to place. And those fluctuations in the density of matter show up in the universe today as temperature differences in the cosmic background radiation and ultimately in things like stars and planets and galaxies.
I think it is incredible that without these fluctuations in the vacuum, these tiny insignificant things that we take for granted, our universe might really contain nothing. Nothing of interest anyway. Speaking of the vacuum, this episode was supported in part by Dyson, who sent me their 360i vacuuming robot. It's got this little camera on the top that can see 360 degrees around it. Now, it uses that vision, plus some complex math and trigonometry, to work out its location precisely and to figure out where it's cleaned already and where it still needs to clean. It actually makes a map that you can see on your phone using the Dyson app. And you can use that app also to control the vacuum or to schedule it, even when you're not at home. So I, for one, welcome robots taking over the housework. If you want to find out more, you can click the link in the description. So I want to thank Dyson for supporting me, and I want to thank my Patreon supporters, and of course you for watching.